holomorphic curves, Lagrangians, and coherent sheaves.
Okay, so thank you very much for the invitation to speak at this seminar. So indeed, I will talk about holomorphic curves, Lagrangians, and coherent sheaves, and the relations between them in some very specific two-dimensional and three-dimensional geometries, all more or less related to the projective plane, to P2. Okay, so this talk will be based on a series of papers which are already 1 year old, and it's not a fully derived story, but there are some derived aspects to it, so I hope it's appropriate for this seminar. So in this series of paper, one of them was about coherent sheaves, derived categories, stability conditions on the complex projective plane on P2. One of them was about a correspondence between coherent sheaves on P2 and holomorphic curves in the pair geometry P2E, where E is a smooth elliptic curve in P2. And finally, the third paper was about this other side, about holomorphic curves in P2. So the main point of this story was this correspondence between holomorphic curves in P2E and coherent sheaves on P2. And this correspondence has some number of applications on both sides. On the holomorphic curve side, you can get the proof of the so-called Takahashi conjecture on the integral structure underlying Gromov-Wheeler theory of the pair P2E. And on the sheaf side, you can obtain a proof of quasi-modularity for generating functions of Betti numbers of moduli spaces of coherent sheaves on P2. Okay, so I've given quite a number of talks in various places about these applications. But today I will do something different, slightly different. My main goal in this talk is to describe an heuristic explanation for why you would expect such correspondence between these two sides. Again, holomorphic curves in P2E, where E is a smooth elliptic curve, and coherent sheaves on P2. And this heuristic explanation will rely on two main facts. One of them is hyperkähler rotation in real dimension 4, which is a geometric operation which has the property of transforming holomorphic curves into special Lagrangian submanifolds. It will be our first operation. And our second operation is mirror symmetry, which has the property of exchanging Lagrangian submanifolds and coherent sheaves. Or more precisely, the derived Fukaya category and the derived category of coherent sheaves. And each of these two facts is in some sense well known, but the specific combination of them in which I will use them is maybe not so. So in this talk, I will essentially describe a sequence of steps moving from one geometry to one other in maybe not fully rigorous way at each step, but which at the end of the day will convince you that you might expect such relation between these two sides. And then I will state a rigorous statement, a precise theorem expressing this connection. And it's only at the very end of the talk that I will say something about the rigorous proof, which somehow bypasses some of the not so easy to justify step using combinatorial and tropical replacement. Okay, so I start by some extremely simple geometry. I start with a complex projective plane, P2 of complex dimension 2, real dimension 4. And first, I want to think about it in a real way, in a symplectic way. So I view P2 with its standard real symplectic structure. And for this real symplectic structure, P2 admits the T2 Hamiltonian action, so action of the two torus, leading to the standard toric description of P2. In particular, this T2 Hamiltonian action has a corresponding moment map from P2 to P bar, where P bar is what I draw here, is some triangle. I mean interior of a triangle. And over the interior P of this triangle P bar, the moment map restricts to a map from C star squared contained inside P2 to P, and this map is a Lagrangian torus aberration. So this thing is standard toric geometry. You have this base triangle over a point of the interior, there is a 2 torus sitting. And if you look to what happens when you go to the boundary of this triangle, if you go to a point on the interior of a side of the triangle, one of the cycle of the 2 torus shrink, and what remains is only one cycle. And if you go to one of the corner of the triangle, the 2 torus shrink entirely, and what remains as fiber is a single point. And the total space of this vibration is simply P2. And over the interior, you have C star squared, the complex 2 torus, which in this picture is realized as the complement of a triangle of lines in P2. What we really care about is some deformed version of this picture, in which we replace the triangle of lines in P2 by a smooth cubic curve. So it's a genus 1 curve in P2 that I denote by E. And we will replace C star squared, which was a complement of a triangle of line in P2, by a different affine variety called U, which is a complement of E in P2. And the previous toric description of C star squared deform into a so-called almost toric description in the sense of Symington of P2. So the claim is that there is a fibration of P2 over some base B bar, where now B bar is a closed disk. So the triangle of the previous picture have been replaced by a disk. The corner have been smoothed out. And over the interior of this disk, you have this variety U. And in restriction to U, this map is a Lagrangian T2 fibration, except that it's not smooth everywhere, but it has 3 nodal singular fibers. And now if you look to what happens at the boundary of this disk, over a boundary of this disk, you have a cycle. And indeed, the curve, the space sitting over the boundary of the disk, it's a family of cycles, so it's a 2 torus, and it's indeed our elliptic curve E. Is there any question about this picture? So this picture is a description of the complement of P2 minus E as a fibration over a disk, a real Lagrangian torus fibration with 3 singular fibers. And some easy check that this picture kind of makes sense. You can do some easy topological checks, some Euler characteristic computation. P2 has topological Euler characteristic 3. E has topological Euler characteristic 0. So the complement U has also topological Euler characteristic 3. So it cannot be a smooth torus fibration, because if not, it would have Euler characteristic 0. And the fact that there is 3 singular fibers exactly account for the correct topology. Okay, so we'll focus on this affine variety U. And from the way I've introduced U as a complement of an elliptic curve in P2, so from some complex or algebraic point of view, U has some complex algebraic structure coming from P2, and U is some affine algebraic complex surface. And the way I've introduced it, you should think about it as some kind of analog of C star squared, a slightly more complicated affine surface than C star squared, but not so much. And as E is an anticanonical divisor of P2, U admits a natural holomorphic symplectic form that I denote by omega I, which is unique up to scaling. So it's a 2 form on P2, which has first order pole along E, and so which is holomorphic on the complement U. So the conclusion is that U is a non-compact holomorphic symplectic surface, or if you want, in dimension 2, holomorphic symplectic and Calabi-Yau are the same. And I will denote that by U I omega I, where I is really the complex structure, and omega I is the holomorphic symplectic form. So the first side of the correspondence I'm going to describe in this talk is about holomorphic curves in this geometry U. More precisely, we like to study holomorphic curves in U with one boundary living on a Lagrangian T2 fiber. So when I'm phrasing this question, I'm really leaving algebraic geometry. I'm really doing complex geometry because these curves are not algebraic. They're really complex curves with boundary. And I want this boundary to live on a Lagrangian T2 fiber. So the picture to have in mind is the one which is drawn on this slide, where I've again drawn this torus vibration. And I've drawn something in red. And this red, topologically, it's supposed to be a disk, which has a boundary on a smooth T2 fiber, and then which is doing something possibly complicated into the geometry. In particular, it is eating 2 of the 3 singular fibers. So in the case of disk, so of genus 0 curve with one boundary, we look more precisely to so-called Maslov index 0 disk, which are the one relevant for the construction of the mirror of U in the Ströbinger-Josasol picture of mirror symmetry. They're exactly the so-called instantaneous or quantum corrections. So from a dimension point of view, if you do some dimension count, you will see that a generic T2 fiber, so if you fix a T2 fiber of this vibration and you ask, does it bounce such an holomorphic disk? And you will see just by dimension reason that in general it doesn't. So generic T2 fiber do not bound such a disk, and the T2 fibers bounding such a disk from codimension 1 families called walls. Okay, so these things are my starting geometrical objects. This curve with one boundary component living inside U and which has a boundary on a torus fiber. And here on this picture, I draw a disk, but for later purposes, I would also consider higher genus curve. So higher genus curve, so I would have some holes in this picture, but still with a single boundary. Now let me après switch topic. We'll come back to holomorphic curves in P2E in one moment. But for now, let me talk about the mirror. So let me talk about mirror symmetry for this pair P2E. So the mirror of P2 is usually described as being the data of a Laurent polynomial W, so a map from C star square to C, given by the formula xy maps to x plus y plus 1 over xy. So this thing is a Laurent polynomial in C star squared, and it's easy to check that W has 3 critical points in C. It has 3 critical points, and so 3 critical values in C. And it's also easy to check that smooth fibers of W are 3 punctured genus 1 curves. So essentially, if you compute fibers of this map, you find some cubic equation, you find some genus 1 curve, but because we are taking this equation in C star squared, you find a genus 1 curve minus 3 points. So this thing is what I guess most people with in first approximation describe as being the mirror geometry of the projective plane. But in some sense, it is more precisely the mirror of the pair P2D, where D is a divisor in P2 made of a triangle of lines. And what will be of interest for us now is a mirror of P2E, where E is a smooth cubic curve, which is obtained by deforming the triangle of line. And on the mirror side, this deformation of the triangle of line into a smooth cubic corresponds to fiber-wise compactifying the mirror. So you can fiber-wise compactify the fibers of W. I told you that each fiber of W was a genus 1 curve minus 3 points, and you just add these 3 points to fill in and to get compact genus 1 curves. Doing that, you get a new geometry, V, which is a partial compactification of C star squared. And W extends to a map from V to C. And now W is an elliptic vibration because we close up the 3 punctures. And because W had the 3 critical values, this elliptic vibration has 3 nodal singular fibers. And I can show that this geometry can be obtained maybe more directly by starting with a rational elliptic surface, V bar mapping to P1 by some map W bar, where the fiber over infinity is some I9 fiber, a cycle of 9 projective lines. And then you get this geometry V by removing this fiber at infinity. Here is a naive picture. You have some elliptic vibration. So as you probably know, a general rational elliptic surface will have 12 singular nodal fibers. And here I'm looking to a non-generic situation where somehow 9 of them are at infinity and form this cycle of 9 P1s, and I have 3 singular fibers at finite distance. And so this geometry V that I've introduced as being the mirror of the P2E is this elliptic vibration over C when I remove the fiber at infinity. And again, you can check that this fiber that I remove is anti-canonical for the compact geometry. And so this geometry V is also a non-compact holomorphic symplectic surface, or Calabi-Yau surface. And I denote by J its complex structure, and by omega J its holomorphic symplectic form. So what I've done in the previous slides is introducing 2 geometry. Maybe I come back here. So I introduced this geometry U, which was some affine surface, the complement of an elliptic curve in P2, which admits a real torus vibration, a Lagrangian torus vibration with 3 singular fibers. Then I introduced a different geometry, which was this V, which now is an elliptic vibration that I introduced as being the mirror of P2E, and which has 3 singular fibers. So just naively looking at these 2 pictures, they look similar. In both cases, you have families of tori with 3 singular fibers. Except they are different because the map from U to B is Lagrangian, whereas the map W from V to C is holomorphic, which translates into the fact that U and V are very different as algebraic varieties. U is affine, whereas V is an elliptic vibration, so it contains a lot of compact curves, which is not the case of U, compact holomorphic curves. And correspondingly, the natural compactification, complex or algebraic compactifications of U and V that I've introduced are very different. U compactify in P2 by adding a smooth elliptic curve at infinity, and V compactify in V bar by adding some I9 fiber at infinity. Nevertheless, the claim, which in fact is a relatively easy claim, is that topologically, or from the point of view of differential geometry, U and V are the same. The claim is that U and V are diffeomorphic. And in fact, these 2 torus vibrations, U over B and W from V to C, are topologically isomorphic. So this thing is maybe slightly surprising, but it's relatively easy to check when you think about checking it. So now there will be a much deeper fact relating U and V, which is that in fact they're related by hyperkähler rotation. So I remind that the hyperkähler manifold from the, let's say, Riemannian geometry point of view is given by X, a C-infinity manifold, G, a Riemannian metric on X, and a triple ijk of complex structures on X, which form a quaternionic triple. So there are complex structures. So I squared, G squared, K squared is -1. But furthermore, they satisfy quaternionic relations. So K equal Ij is minus Ji, and so on. And the last condition is that this metric G is scalar with respect to each of these complex structure I, J, and K. In particular, you get the triple of Kähler forms, omega I, omega J, omega K, which are the Kähler forms of G with respect to the complex structure I, J, and K. And you similarly get a triple of what I call holomorphic symplectic form. So you get omega I, big omega I, which is omega j plus I omega k, which is holomorphic in the complex structure I. And similarly, you get big omega j, which is holomorphic in the complex structure j, and big omega k, which is holomorphic in the complex structure k. And in general, if you have some hyperkähler manifold, and if you look at the various complex manifolds that you get for various complex structures, so xi and xj, for example, they can look very different. Some very simple example, if you take E, an elliptic curve, a smooth genus 1 curve, and if you look to E cross C, then there is a flat Riemannian metric on such a thing, which after hyperkähler rotation becomes C star squared. You see from the complex or algebraic point of view, E cross C and C star square are very different. C star square is affine, E cross C is not, but still they are both obtained as from different complex structures on the same underlying manifold. Okay, from the topological point of view, these two varieties are just R2 times T2. And now the story I'm going to describe is simply, not so simply, but is a variation of this example. C star square is some hyperkähler rotation of E cross C, and now we replace C star square by this variety U, and I replace E cross C by V. And the claim, which is a quite recent theorem due to Collins, Jacob, and Lin, is that the two varieties I've introduced, Ui omega I and Vj omega j, are hyperkähler rotation from each other. So it's a much stronger claim than the claim that they are diffeomorphic. It's a claim that there is a particular non-trivial hyperkähler metric on this manifold, and that these two complex structures are both compatible, are both Kähler with respect to this metric. And so as corollary of this claim, you get a proof of the fact that if you start with an elliptic vibration, the W from V to C, and if you hyperkähler rotate it, you get a special Lagrangian vibration on U. And in general, it's a very difficult task to construct a special Lagrangian in symplectic geometry. And one of the few tools existing, if you're in a hyperkähler rotation, if you're in a hyperkähler situation, is to hyperkähler rotate some holomorphic vibration. And here you can do that. And here I'm not fully precise in the statement of the theorem. I need to be slightly careful because there are various moduli on both sides. There are complex moduli and Kähler moduli, and I'm not telling you precisely how they match. But the precise version of the theorem is that there is one way to match moduli such that the statement holds. Are there any questions about this statement? So I introduce this two geometry, U and V, and I've stated the fact that they are hyperkähler rotation from each other. Okay, so now coming back to our starting point, which was holomorphic curves in U, we will be able to use this hyperkähler rotation statement to transform our holomorphic curves in U into something else in V. And when you hyperkähler rotate holomorphic curves, you will get special Lagrangians. So here I just recall that more generally, if you're in a Calabi-Yau situation, so if you have a manifold Riemannian metric, some Kähler form, and some holomorphic volume form, which define a Calabi-Yau manifold, then a special Lagrangian submanifold L of M is a submanifold, which is Lagrangian, which means that if you look to the Kähler from omega, and if you restrict it to L, you get 0. But furthermore, it satisfies a special condition, which is that if you look to the holomorphic volume form, and if you restrict it to L, it has to be a constant multiple of the volume form defined by the metric. And we say the special Lagrangian is of phase theta if this constant multiple is exponential at theta. And it's a general fact that hyperkähler rotation rotate holomorphic curve in U with boundary on a T2 fiber, which was the thing I was caring about before, my red curve, if you apply the hyperkähler rotation operation to these objects, the claim is that the resulting things are special Lagrangian submanifolds in V. And if you go through the hyperkähler rotation business, you see that you get special Lagrangian of a specific phase theta equal pi over 2. So you see in this operation, something funny is happening. Here, I add some T2 fibration where the fiber were Lagrangians, and in red, I had some holomorphic curve. And this picture was inside U. And now, after hyperkähler rotation, the T2 fibration has become a holomorphic fibration. So now the torus are holomorphic, and my holomorphic curve are turned into a Lagrangian object, this green thing. So now I have some special Lagrangian into this elliptic fibration with one boundary living on one elliptic fiber. Now is almost the last step, maybe the next to last geometrical step. Now that, okay, so the idea is that we have this Lagrangian in V, but this Lagrangian has one boundary. And we don't really like Lagrangian with one boundary, we prefer closed Lagrangian, so we like to close this Lagrangian in some way. And in symplectic geometry, there is a standard way to do that, which is called the suspension operation. So if you fix a point W in C that you think at the base of this map W, then you can construct a threefold IW as being the set of points UVP in C cross V, given by the equation UV equal W of P minus W. It's an explicit equation. And you can check that YW is a non-compact Calabi-Yau threefold with a volume form given by omega IW equal du over u wedge omega j. And by construction, it has a map over V. And this map is rather simple. It's simply a fibration in affine one-dimensional conics. So if you're over a general point of V, the fiber of this map is given by UV equal a constant. So it's a copy of C star, or topologically just a cylinder. But if you take a point over inside this fiber over a small w, then the equation of these of the fiber of this map become UV equal to 0, and so you get singular conic. You get this singular cone. So geometrically, Y is the fibration of a V, and general fiber is a smooth cylinder, but over a specific fiber, it's a family of cones. And now, if you take this specific fiber where you get cones, if you take it to be where your open Lagrangian is ending, then there is a natural way to construct from it a closed Lagrangian in Y. So we start with a Lagrangian in V in the surface, a two-dimensional Lagrangian in the surface with one boundary. And then we have this bigger geometry, this three-dimensional geometry. And then the claim is that there is a way to lift it, to lift the open Lagrangian into a closed Lagrangian into Y. So the thing to understand is this very simple geometry, which is that if you look to S3, so this thing will be some kind of local model for what's happening. So if you just look to the 3 sphere, if you think about it as a set of points Z1, Z2, and C2, such that modulo of Z1 squared plus modulo of Z2 squared is 1, then this thing has a natural map over the interval 0, 1, mapping Z1, Z2 to modulus of Z1 squared. So this gives you a presentation of the 3 sphere as a fibration over the interval where the general fiber is a 2 torus, But at one end of the interval, one of the cycle of the torus is shrinking to a point, so you only get a cycle. And the same thing happened on the other end, except the two classes of the cycle are exchanged. So you see what happens locally on these. Let me look at the left side. If I look to the green part of the picture on the left side, you get some two-dimensional thing with a boundary over zero. The fiber over zero is the green cycle. But in the full three-sphere, the full three-sphere does not have any boundary over zero. The point being that if I look to the other side or to the other cycle, the right cycle, it shrinks to a point over zero, and globally you get a three-dimensional geometry which has no longer any boundary. Which means that if I do exactly this operation, I start with my green Lagrangian with a boundary, and if I do this operation of adding a three-dimensional geometry, I add these cylinders. And if I multiply my Lagrangian by the cycle containing this cylinder, because this cycle is shrinking to a point over the fiber where my Lagrangian had a boundary, the resulting three-dimensional Lagrangian will have no boundary. And the local description is given by this very elementary example. Okay, so here is the same thing again. So in green, I have my Lagrangian. Over every point, I have my new geometry Y, which has a fiber cylinder. And it's only over the fiber where my Lagrangian has the boundary that the fiber is singular and is a cone. Okay, so if I summarize, at the beginning, I was starting with a red holomorphic curve with one boundary. After hyperkähler rotation, I'm getting some Lagrangian with one boundary. And after this suspension operation, I'm getting a closed Lagrangian, now in a non-compact three-dimensional geometry. Now I arrive to the last step, which is mirror symmetry. So the slightly miraculous fact is that the geometry I've introduced is YW, that I've introduced by this suspension operation, is known to be the mirror of KP2. So now Y is of dimension 3. We went from dimension 2 to dimension 3 by this suspension operation. And the claim is that it's mirror to another non-compact Calabi-Yau threefold, which is KP2, which is the total space of the canonical line bundle O minus 3 over P2. And now I have finally something derived to say because I want to state homological mirror symmetry, which here will be telling me that if I look to the bounded derived category of compactly supported coherent sheaves on this KP2, it will be equivalent to the compact derived Foucault category of this non-compact Calabi-Yau threefold YW, which again is this fibration in half and convex over an elliptic fibration. And in fact, this homological mirror symmetry statement is essentially known and is due to side. So I need to say something more to be able to follow the geometric objects we care about. Because you see, the geometric objects we care about, first they were disk with boundary over a specific fiber over a point W in the base. Then they became Lagrangian with still a boundary over a specific fiber over a point W in the base. And then to close this boundary, I constructed a three-dimensional geometry which depends on W, because W tells me where my bundle in affine convex is degenerate. So when I move W, I'm moving the complex structure of YW. So from the symplectic point of view, YW does not depend on W. They are all symplectomorphic. So in particular, the Foucault category does not see W. So W, as I say, is really a complex moduli of YW, which in fact is mirror to the Kähler moduli of KP2. And the notion of special Lagrangian certainly does depend on W, because as I remind the definition, in the definition of special Lagrangian, you need to use not just the Kähler form, not just the symplectic form, but you need to use the holomorphic volume form, which certainly depends on the complex structure. And so to be able to see what our object, what is special Lagrangian in YW becomes through homological mirror symmetry, you need to know what is the meaning of this W and of special Lagrangians from a categorical point of view. And now there is a general expectation, going back to Thomas and Yao, which is that the choice of a complex structure moduli on a symplectic manifold, so in our case is point W, should define a Brejneron stability condition on the derived category, on the derived Fukaya category of YW, whose stable objects should more or less be special Lagrangians in YW. And in this the prediction is that the central charge defining the Brejneron stability condition should be given by this very simple formula. If you have L a Lagrangian, then Z of L should be given by the integral of the holomorphic volume form omega YW over L. And in particular, the phase of the special Lagrangian, which is usually viewed as a geometric property of special Lagrangians, coincide with the phase of the central charge in the sense of Brejneron stability conditions. So the conclusion is that under mirror symmetry, you should get an embedding of the space of points W in C inside the space of Brejneron stability conditions on the derived category of current sheaves on Kp2, such that special Lagrangian submanifold of YW of R theta, which are the kind of objects we care about, correspond to W stable objects in this derived category of current sheaves with respect to the corresponding Brejneron stability. And if you go through the mirror symmetry dictionary, you expect that the regime where W is large, so on this base, when W is really, if you think to this thing as being a disk, W is really close to the boundary of the disk, you expect this limit to correspond to the geometric limit. So if you want the large volume limit from the Kp2 point of view, where you expect your stability condition to reduce to geometric notions of stability, such as slope or Giesecker stability for current sheaves. Okay, so here is a summary of the list of steps I went through. I started with holomorphic curves in U equal P2 minus E in the complement of a smooth genus 1 curve with boundary on a special Lagrangian T2 fiber. After hyperkähler rotation, I got an open special Lagrangians of phase pi over 2 with boundary on the elliptic fiber, so a specific elliptic fiber of this elliptic fibration W. After this suspension operation, we got a closed special Lagrangian of phase pi over 2 in this non-compact Calabi-Yau threefold YW, obtained by suspending the elliptic fibration. And finally, applying mirror symmetry, homological mirror symmetry, we should get W stable objects of phase pi over 2 inside the derived category of current sheaves on P2. So you see there is something slightly strange in this sequence of steps, in the sense that we start with something which is essentially P2 minus E. Then after hyperkähler rotation, it does no longer seem to have any clear relation to P2. But after this suspension and this mirror symmetry operation, we go back to P2. So at the end of the day, you get a prediction that there should be a relation between holomorphic curves in U equal P2 minus E and stable objects in the derived category of sheaves on Kp2. And you can check that this correspondence makes sense in the sense that it's compatible with natural notions of wall crossings on both sides of the correspondence. If you look to holomorphic curves with boundary on a T2 fiber, when you move this T2 fiber, you expect this count of holomorphic curves to jump and to exhibit some wall crossing phenomena. And in a parallel way, from the point of view of stable objects in the Dirac category of sheaves, similarly, when you move the stability conditions, you expect a wall crossing for stable objects. And the claim is that in the correspondence I've described, the choice of the T2 fiber on the starting geometry ultimately correspond to choice of stability condition on the Dirac category on KP2. And so these two wall crossing phenomena are compatible. So I should say that in the step I've described, to be able to precisely follow all objects is quite difficult, in particular if you want to make some precise statement about numerical counts of such objects. And but it's possible to make a precise mathematical theorem in some appropriate limit. More precisely, I will focus on the case where the fiber W I'm talking about is very close to infinity. So in my original geometry, where U was a complement of an elliptic curve E in P2, I had this picture, I have this blue elliptic curve at infinity sitting over the boundary of the closed disk, and over the open disk, I have my geometry U, which has this torus vibration. And I was looking to holomorphic curve in red with boundary on such a torus fiber. And it's quite difficult to make precise counts of open holomorphic curves. But in the limit where the torus fiber is really close to the elliptic curve, at least intuitively, you can imagine closing up the open curve into a closed curve by gluing a small holomorphic disk touching the elliptic curve E in a single point, as on the picture. And the idea should be that if the elliptic curve is very close to the boundary, there should be almost no choice for what you are gluing into. So there should be a natural way to do that. So the conclusion is that if the T2 fiber is really close to infinity, then you should be able to turn your open holomorphic curve into a closed holomorphic curve, touching the elliptic curve in a single point. And now once you are working with closed holomorphic curve, you are back into algebraic geometry. Now you can talk about this closed curve will be algebraic, and then you can use some algebraic machinery to talk about these objects. Whereas if you were looking to open curves, you would have to deal with complex analytic or symplectic geometries, which would be much more certain. So the upshot is that here we look to this count of red curve. So now closed holomorphic curve in P2, touching the elliptic curve E in a single point. And using an algebra geometric machinery of relative Gromov-Huygens theory, it's possible to extract numbers, to extract invariants, counting these curves. So for every d, some degree, we'll look to degree d curve in P2, meeting the elliptic curve in a single point, and I will look at genus G, such a curve. And here I'm skipping some details, but the claim is that using relative Gromov-Huygens theory, you can define some numbers, NGD. And now if you believe the previous sequence of steps, NGD are a precise version of this count of holomorphic curves. And at the end of all these steps, we have some count of current sheaves. So if you believe all these steps, you should expect this number NGD, this relative Gromov-Huygens invariance, to in fact to be equal to some count of current sheaves. And so here is a claim is that for W large, which was the limit I'm considering here, holomorphic curve wrapping the collapsing cycle of T2 correspond to one-dimensional current sheaves on KP2. So here maybe I should have been more precise. You see that this operation of gluing a disk to close the open curve is only possible if the C cycle on the T2 is topologically contracted to a point when you go to the elliptic curve. And if you look to the first homology of this elliptic curve, it's of rank 2, and one direction is contracted, but the other is not. So I can do this operation of obtaining closed curve from open curve only for this particular class of the boundary, the one being contracted to a point on the elliptic curve. And if you go through the sequence of correspondence I've described, the claim is that this first homology of the torus fiber of the T2 on the coherent sheaf side is identified with a set of degree and rank of current sheaves on P2. And restricting the attention to curve wrapping the cycle being contracted to a point on the elliptic curve correspond to restricting your attention to rank 0 sheaves on P2. So sheaves supported on curve on P2. So now I want to define precisely some numerical invariant on this sheaf side. And as I said, here I'm looking to W large. And on the stability side, you expect this W large to correspond to the large volume limit. So you expect the notion of stability to reduce to the ordinary Giesecker notion of stability for current sheaves. So you can look to MD, the moduli space of Giesecker semi-stable current sheaves on P2, supported on degree D curve. So this thing is a projective variety of dimension D squared plus 1, and I will look to the Betti numbers of this projective variety. And here in the way I've written this slide, I made some oversimplification to get a nice moduli space. I mean, you also need to fix the holomorphic holocharacteristic of the sheaf chi. And for different value of chi, you get different moduli spaces. But let me skip over this point for now. Essentially, what I will do precisely is to take an average over the different possible value of chi. So in first approximation for every D, you look to the moduli space of current sheaves on P2, supported on curve degree D, which are Giesecker semi-stable. And you look to the simplest topological invariance of this moduli space, you look to the Betti numbers.
May I ask a question?
Yes.
How did you pass from the sheaves on a total space of O-3 to the sheaves on a P2?
Yes, so the claim is that for the kind of sheaf I'm looking there, so essentially sheaf which have, let's say, either non-zero degree or non-zero rank, then the claim is that Giesecker semi-stable sheaves on KP2. Okay, maybe I should be more precise. When I say rank, I always mean from the P2 point. So first on KP2, I'm looking to sheaves with compact support only. And the claim is that if I look to such a sheaf, and if it's Giesecker semi-stable, and if it has a non-trivial C1 or C2, then it is push forward of a Giesecker semi-stable sheaf on P2. So in fact, looking to moduli space of Giesecker semi-stable object on P2 or on local P2 are the same. And to get this statement, it's crucial to use the fact that KP2 is O-3 and it's negative enough. Essentially, the proof that the two moduli space are the same uses negativity to get some vanishing, which ensure you that, for example, your shift does not have any non-trivial thickening your sheaf could be set theoretically supported in P2, but not scheme theoretically. The support could be thickened in the local P2 direction. But the claim is that if your sheaf is Gieseker stable, it does not happen. So the conclusion is that you can think about moduli space of Gieseker stable sheaf on P2 or on local P2, and they are the same. And obviously, this argument breaks only in one case if you look to skyscraper sheaf of points. Because for skyscraper, let's say skyscraper sheaf of 1 point, on P2, the moduli space will be P2, and on local P2, the moduli space will be local P2, which are obviously the same. But the argument I was talking about previously breaks only in this very specific case. So for here, what I'm looking at, there are sheaves supporting on degree D curves. If D is non-zero, then moduli space of such semi-stable object on P2 or local P2 are the same. Okay, so here is a imprecise form of the theorem, which is that the data of this relative Gromov-Witten invariance NGD of P2 relatively to the elliptic curve should be equivalent to the data of these Betti numbers of moduli space of coherent sheaves, one-dimensional coherent sheaves on P2. So I should stress that the two sides of this correspondence looks quite different. Like on the Gromov-Witten side, to even formulate the question, you need to fix the elliptic curve and then to count holomorphic curve with tangency conditions along the elliptic curve. Whereas on the sheaf side, we don't talk about elliptic curve. You look to all possible coherent sheaves on P2 and all possible and corresponding moduli space. So in some sense, what I'm trying to say is that the objects which are counting on both sides, in some sense, live in different geometry. So both are obviously related to P2, but the Gromov-Witten side is very related to the pair P2 with the elliptic curve, while the sheaf side is only about P2. And in fact, there is a precise version of the theorem, which is a precise identity of generating series.
May I ask another question?
Yes.
How do you match the virtual classes on both sides?
Yeah, so somehow the statement will be a numerical statement. And in fact, so I will say a few words about the proof, but I don't know a proof like which goes through comparing moduli spaces. And you see, even the parameters parameterizing the problems on both sides are different. On the Gromov-Witten side, I have a parameter parameterizing the genus of the holomorphic curves, whereas on the sheaf side, I don't have such parameter. And conversely, on the sheaf side, I have some cohomological parameter. I am looking to Betti numbers. So in some sense, these Betti numbers are already more refined than the virtual class. It's not possible to interpret them as coming from virtual class as some kind of refined invariant. So I have this J, which is some cohomological parameter, which again does not have an obvious interpretation on the Gromov-Witten side. So what I'm trying to say is that it's not known how to compare these two sets of numbers by comparing moduli spaces of the two kind of objects. Simply because first, the numerical, like the discrete parameters on both sides are different, and these show up in the precise version of the statement, which is that in the precise version of the statement, there is a very non-trivial change of variable. This is y equal exponential I h bar. So I told you that on the Gromov-Witten side, there is a genus parameter. And so here in the generating series, I've introduced a formal variable h bar, chemical of the genus. And also on the sheaf side, there is some cohomological refinement. I'm looking to Betti numbers. And so there is a corresponding variable y in the generating series. And the claim is that to get an equality, you need to do the very non-obvious change of variable y equal exponential I h bar, which has no obvious geometrical interpretation.
But does the correspondence between the holomorphic curves and the sheaves hold on the level of moduli spaces, or just like set theoretical correspondence?
Yeah, so my statement is at the numerical level. And at the level of moduli space, I don't even know a precise statement that you might conjecture.
But previously you stated that there is a correspondence between the two. So what did you mean then exactly?
Yeah. So I will come back to this point at the end, which is that in this correspondence, you should think about all these steps as being somehow heuristic. It is what I announced at the beginning, as this thing is somehow heuristic, and at the end I will explain where are the difficulties to make these statements precise. So I will come back to this point at the very end. So the claim is that this sequence of geometric steps, you can use them to guess that there should be a relation between maybe these numbers, but I don't know how to make it precise enough first to prove the theorem and then to get a more precise statement at the level of moduli spaces. So all what I've described is geometric correspondence, where only some kind of motivation for why such kind of theorem, which is the precise theorem that I've studied here, might be true. But as I will explain at the very end, so in 2 minutes, it's not enough. And as I said, so the proof somehow does not use all the sequence of geometric correspondence I presented before. And the proof goes through essentially tropical geometry. The idea is that essentially you can tropicalize holomorphic curves in U, in this torus aberration, into some kind of graph on the base of this torus aberration. And then you can show that these counts, this chromorphic count NGD, can be algorithmically reconstructed in terms of something called a scattering diagram, in terms of graphs drawn on the base of this aberration. Here is a picture of this algorithm. And the main result to give the proof is to recover this tropical algorithm. So here you have graphs which appear at tropicalization of holomorphic curve. And to prove the theorem, you need to understand what is the meaning of this graph on the coherent sheaf side. And as I explained before, in this correspondence, the base of this aberration should somehow live in the space of bridge-general stability condition. So somehow this graph should be drawn in the space of stability of bridge-general stability conditions. And here the precise statement is that it's possible to do that. It's possible to construct this scattering diagram inside the space of bridge-general stability conditions, so that the rays of this picture, so these graphs, correspond exactly to stability conditions for which there exist stable objects of a given phase pi/2. And from the stability point of view, everything is algorithmically reconstructed using the Contevi-Saberman wall crossing formula from the line bundle O of n. And so here there is another technical thing that I'm skipping, but which is related to the previous question, because between P2 and local P2, somehow here it's crucial that even if you think about the invariant are being attached to moduli space of sheaves on P2, you really think about them as being attached to local P2, which is a Calabi-Yau-3 situation, in which there is a general machinery of Contevi-Saberman wall crossing formula for DT invariance of Calabi-Yau threefold, which will tell you how things vary when you vary the stability condition. Maybe I skip this remark and I just end by maybe a more precise answer to the question, which is why the sequence of geometric steps I've described is not enough to get the rigorous proof. So the rigorous proof uses some kind of alternate path through tropical geometry. But the goal of this talk was to present this sequence of geometric steps because it's really a natural geometric way to understand why such relation might be true. So the first difficulty is that at the hyperkähler rotation step, I said naively that holomorphic curves become special Lagrangians. But holomorphic curves, if I really think about them in a Gromov-Witten way, they are really holomorphic maps. In particular, they do not have to be immersions, they can have multiple covers, and you need a virtual class to count these numbers in a virtual way. And similarly, special Lagrangians, should also be counted in an appropriate virtual Donaldson-Thomas way. They're really common family, and to exact numbers, you also need to do some virtual work. And so when I say that you go from one to the other by hyperkähler rotation, the comparison between the two is quite non-trivial, and is related to the presence of this Chandler variable y equal exponential ah bar in the theorem. So what I was saying is that by hyperkähler rotation, at the naive level, if you forget all virtual difficulties, you might believe that the holomorphic curve turned into a special Lagrangian. But in fact, so in my precise theorem, there is some much more precise statement, which is telling you that if you look to holomorphic curve, and if you count them in a virtual Gromov-Witten way, in some way, after hyperkähler rotation, they are related to appropriate virtual count of special Lagrangians, but in a very non-trivial way. And in fact, I claim there is a previous example of this phenomenon, which is to look at the local situation of a compact Riemann surface C. And in this case, it's known by the work of Chong, Diagonescu, Pan, that the weight polynomials of the GLN character variety of C, that you should think about it as being the local contribution of C to count as special Lagrangians in the Fourier category, are related to higher genus Gromov-Witten theory of the local curve, OC plus KC. So here I'm looking to some of simpler geometry, just a single curve, and try to do the hyperkähler rotation for like the canonical bundle of this curve. Applying the naive argument, you expect to be able to relate Gromov-Witten theory of this curve and the geometry of special Lagrangian, which in this case reduced to the geometry of local systems, so just the character variety. And this local example is known, it was known before that there is such relation, but even in this simplest case, there is no geometrical understanding of why the precise relation has a precise form it has. So certainly it's something which maybe at some point will be understood better, but for now it just does not have really good conceptual explanation. Okay, I will stop there. Thank you for your attention.
Okay, thank you very much for this very nice talk. So please, participants, thank Pierrick in the chat if you like the talk. Right, and also, okay, so are there any questions? You can use the chat or turn on your microphone.
And so what about other Fano surfaces?
Was there what? Sorry.
I mean, if you consider some other Fano surface,
yes.
Would you expect to?
Yeah. So for example, if you go through a sequence of heuristic geometric steps, if you replace P2 by a Del-Pezzo surface and E by some smooth anticanonical divisor, you expect everything to be the same. And in fact, in some of my papers, I've written the analog of the theorem as a precise conjectures for all Del-Pezzo surfaces. And but I only proved it for P2, and I did not prove it for general Del-Pezzo surfaces, because even if the general strategy I'm applying to proving it in P2 somehow should extend to other Del-Pezzo surfaces, there are some, it's just more difficult because, you know, higher Del-Pezzo surfaces have a bigger H2, there are more curve classes, which is related to the fact that the moduli space of stability conditions is of bigger dimension. And so the short answer is that the heuristic description apply to Del-Pezzo surface, and I conjecture that the precise statement I've written here should hold for all Del-Pezzo surfaces, but I did not prove it for all Del-Pezzo surfaces. I only prove it for P2 because it's technically easier. But I expect it to hold.
Thank you.
Any more questions to Pierrick? So can I ask? So you have this moduli space MD that yes. you had. So what is known about this? So those Bethe numbers, for example, are they known?
Yeah. So I think in some sense they are not known. I mean, so So for example, I mean, as consequence of the proof I've given of these correspondence, as some kind of aside of the proof, I've given some algorithm computing these Betty number of this moduli space MD. And okay, maybe the simplest possible answer is that I don't know like alternative algorithms. So there are some numbers I've computed which were never computed before, as far as I know.
So did people study this space before, or it showed up in your work?
Yes. So certainly, I mean, this space was first introduced by Le Potier in the 90s, and it was, I mean, various things were known about it, and in low degree it was studied. And maybe I should say, so here I'm slightly lying. There was this warning sign, which is in fact the moduli spaces are really moduli space MD chi. They not only depend on D, they also depend on chi, which is a holomorphic Euler characteristic of the sheaf. And for example, when D and chi are co-prime, the moduli space is smooth, and I'm really looking to Betty numbers. But when D and chi are not co-primes, this moduli space is singular. And in fact, what I'm really looking at are like Betty numbers of the intersection cohomology of these Betty numbers. And so when D chi are co-prime, so when MD chi is smooth, it was computed like in low degree, like maybe until degree 6 or 7. These Betty numbers using various techniques were computed. But for example, computing the intersection cohomology of these spaces, so when these moduli space MD chi are singular, thing was just never been done before, because you just need different tools to address the singularity. So I mean, most of the low degree computation were done by like some kind of explicit study of the geometry, where somehow what is involved in the proof of the main result is some kind of very general like wall crossing type argument, which somehow is systematic and I will apply in full degree in a systematic way. And in fact, even if this moduli space is only about curves supporting on, sheaves supporting on curve degree D, in fact, the algorithm also compute Betty numbers of moduli space of any kind of current Gieseker semi-stable sheaves on P2. So not just supporting on curve, but of rank 1, rank 2, of any rank. And maybe, so these moduli spaces of sheaves of positive rank have been studied much more than the one of rank 0, supporting on curves. And there are alternative way to compute these invariants. Like it's possible to blow up a point and do some wall crossing on P2 blow up in some point. So what I'm trying to say is that the case of sheaves of a positive rank on P2 have been quite studied. The case of sheaves supporting on curves have been studied, but less. And some of the algorithm I'm producing in this proof just compute all these Betty numbers in a different way. So in the case which was well studied, it's a different way to produce it. And in the case which was not well studied, it's a way to prove what I need for the main statement I explained.
Yeah, thank you. That's very interesting. So any more questions to Pierrick? Okay, if not, yeah, so thanks once again for the great talk. And we'll be moving to the ICMS chat room, and someone will post the link in the chat. Maybe it will be me.